the afternoon session. So the first talk today is going to be by Joris Witstok, who is a PhD student at the Kavli Institute for Cosmology at the University of Cambridge. And he will be talking about some high redshift stuff about the Epoch of Reionization and uncovering the physics of star formation.
Yeah, so thank you, Abhijit. And first of all, thank you to the organizers for putting up this really nice conference and giving me the opportunity to talk about this work today. So yeah, as you mentioned, I'll be talking about the physics of star formation in the very early universe, doing this by two of the main far infrared emission lines, C2 and O3 at 158 and 88 micron. So first of all, just a very brief introduction about why we're interested in this period of the universe. So the Epoch of Reionization started at a redshift of about 20 to 25, all the way when the first objects, so the first stars and galaxies started to form. And we know it ended at a redshift of about 6. And the motivation here is to study this process in detail and see how the universe exactly was reionized. So the way we usually think about this is through this model. And I should say here that the current consensus is that galaxies were really the main driver behind this process of reionization. So the way we think about it is we split the number of ionizing photons that are being produced up into 3 different factors. So first of all, we consider the UV luminosity density. So just observationally, we look at how much star formation can we directly observe. Then there's this Psi-ion factor, which just tells you how efficient those stellar populations are at producing ionizing or Lyman continuum photons. And then finally, there's this F-escape, which tells you how efficiently the photons can escape the galaxy. So schematically, you might think about something like this, where a stellar population is producing Lyman continuum photons, which then have certain escape channels from the galaxy to ionize the neutral IgM. And then finally, I should say that you also need to consider on a cosmological scale the recombinations, which has to do with the density and temperature of the IgM. So that's when you usually turn to cosmological simulations. But here I'll mostly be focusing on the actual galaxy properties of star formation. So these 2 factors here. So then if we really want to study these in detail, we have to do spectroscopic studies. So look at galaxies individually and their spectra. So from the ground, at least, so before we have access to James Webb, if we want to look in the rest frame optical, we're really restricted to quite low redshifts. This is what I consider relatively low redshift, so below 3.5 or so. And then if you go to the rest frame UV, the brightest line there, Lyman alpha, you can really only observe consistently at least up to a redshift of about 7 when it starts to get absorbed, just like the ionizing photons, because the neutral hydrogen. But already with ALMA, we have these really powerful tracers, the C2 and O3 lines in particular, where we can already look quite deep into the Epoch of Reionization. So just to make that point a little bit in more detail, if we look at the redshift of several lines and where we observe them, you've got all the rest frame UV lines here, which you can see from the ground over a large redshift range. Then the optical lines are restricted until we get the first data from James Webb. But already with ALMA, we have this whole new observational window with all these far infrared lines that we can observe. And so just to give an example, apart from, so Lyman alpha is usually the line that's being used to spectroscopically confirm high redshift galaxies so far, but already there's about as many confirmed with ALMA through the C2 line, which Sander has talked about on Wednesday, if you want to have a look at his talk. So then, of course, you all know with ALMA, you also get these beautiful spatially resolved data sets. So you don't just get a spectrum, you also get information about the spatial structure. So in this talk, I'll be focusing on 4 galaxies at a redshift of about 7, which has been spectroscopically confirmed with C2, and then followed up with OIII 88 micron, and in one case also the nitrogen 205 micron line. So these galaxies are very UV bright. They're for this redshift normal star-forming galaxies with stellar masses of about 10 to the 9, and then they've got medium to high equivalent widths in the optical lines, which were crucially used in the selection of these objects. Through the Spitzer photometry, you can really accurately constrain the photometric redshift, which then allows ALMA to very efficiently scan for the C2 line. So just a first look at some of the data. Here I'm showing the OIII contours in red on top of new very deep HST rest frame UV images. And both of these, so OIII arises from very high ionized gas. So you expect it to trace the rest frame UV, which is showing you the star forming regions. And we do see this as mostly the case. Interestingly, though, you see these 2 components. The OIII really only centered on this one portion in this source. So it traces it, the OIII traces the rest of UV well, but not perfectly. And then I'll also quickly mention with ALMA, you get, of course, automatically the dust continuum as well. So for these sources, we don't actually detect the dust continuum at 90 microns, but we can still get some very interesting constraints from this, and I'll talk about this in the last part. So first I'll focus on the 3 emission lines, or the 3 traces of the interstellar medium. With C2, due to its ionization potential just below that of hydrogen, we expect this to come, well, either from ionized or a neutral gas, really. But in this case, we have actually established it's produced mostly in neutral gas, whereas the nitrogen and oxygen lines, which have higher ionization potentials, especially oxygen 3, should come from very highly ionized gas. So why do we know C2 is mostly produced in neutral gas? Well, if you look at the ratio of C2 to N2, here as a function of just the total far infrared luminosity, you expect this ratio to be quite low if most of the C2 is produced in ionized regions, because there you also expect to see nitrogen 2. So you get sort of these values indicated by the blue region. But our upper limit actually suggests that some of the C2 should also be produced in these neutral, probably photodissociation regions, which then don't produce any nitrogen. Okay, so moving on to the oxygen 3 and C2 lines, just if we focus on the top panel of this figure first, this is showing the line ratio as a function of the equivalent width of the optical lines. And so this is really just an inverse tracer of the age of a starburst. And we see there's quite a clear positive correlation here. So this is both for our sources, as well as in the background, local metal poor dwarf galaxies. And if we look at some simple cloudy models, indeed we see that in order to get to these, to reproduce these values, we need quite a young stellar population and a pretty high ionization parameter, as you may expect. But then if we actually look in more detail at the oxygen 3 line over here, normalized by the star formation rate, we see our values seem to be quite high already compared to the local metal poor dwarf galaxies. And if you look at models, you actually only can really reproduce them if you use a almost solar metallicity. So these orange lines are, first of all, have an enhanced alpha element abundances. And secondly, so the total metallicity is getting very close to solar. And this is really quite strange if you think about it, because these systems at Redshift 7, the universe is less than 1 billion years old. And so you don't really expect to see metallicities that high that early already. So if you look at, for example, the fundamental metallicity relation, this is telling you basically in the local universe, given a stellar mass and star formation rate, what metallicity do you expect? For a 10 to the 9 solar mass galaxy, you expect much, much lower metallicities typically. But however, there are also some indications this might not be so surprising given the recent metallicity calibration, for example, using OIII. And there's been also some other indications in, albeit slightly higher stellar mass systems, where they've also found near solar or even supersolar metallicities. All right, so finally, just quickly, I'd like to show some of the spatial structure in our sources. So we see both a range of global O3 over C2 ratios, but also if you look at the spatially resolved ratio, you can see, for example, we see this sort of gradient in the source going from about 2 to almost 10 and above. And interestingly here, you can see that peak of the dust emission actually seems to sort of line up with the lower line ratio locus. And we looked at this a little bit more quantitatively. And so the line ratio as a function of the dust obscuration, which is here measured through the IR over UV luminosity, we see both in the global, local, and also these local galaxies, we see an anti-correlation between the two quantities, suggesting that you get these very high line ratios in not so dust obscured regions. So these are probably very young and likely, not so dust obscured star forming regions. Then very quickly to talk about the dust emission we see. So why is this interesting to look at this high redshift? Well, as I mentioned, these systems are so young that there's just not that much time for metals and therefore for dust to build up. And so you can really constrain the formation processes. And also we expect to see higher temperatures towards higher redshifts, because higher redshift systems will have more young, massive stars that will heat up their surrounding dust. And so you just expect a globally warmer dust temperature. So in this figure, I'm showing exactly that relation. So the dust peak temperature as a function of redshift is shown here. And indeed, from, for example, these models shown by the lines, you can see we expect higher temperatures early in the universe. And I'd just like to point out, all right, thanks, that's perfect. So just like to point out this one system that we looked at, the blue point here, where we measure through the non-detection at 90 microns, we can actually exclude a lot of the high temperature solutions, which suggests that we have this really low dust temperature here. And this is not actually, it's low compared to all the other high redshift ALMA dust detections. But this has been seen before in one other source here at slightly lower redshift. And so this is just very interesting, I think. There's no real consensus here, but we really need to have a more careful look at what's happening with the dust at these early times here. And that source in particular, actually, a low dust temperature also means a very relatively high dust mass. And therefore, this is suggesting we need to invoke a high, first of all, metal yield to even produce the dust. And then also dust producing sources have to have a high dust yield. So for example, supernovae, which are thought to be the main source of dust on these short time scales, we see the yield they would need to produce is actually pushing against the theoretical limits. And so we might have to look at even other mechanisms to produce or grow dust, and perhaps a top-heavy IMF to explain the high metallicity again. So I'll just conclude here saying that we've detected oxygen 3 and C2 in these 4 star-forming galaxies at redshift 7, seeing a diverse and also spatially varying ratio, and a tentative anti-correlation with the dust obscuration. We've also looked at a trend with the equivalent width of the optical lines, which are an inverse age tracer, which we also see in local metal-poor dwarf galaxies. And surprisingly, we need this near solar metallicity to explain the oxygen 3 luminosities. And finally, we've looked at the dust SED, seeing for one source particularly low temperature and high dust mass, which would imply we need a very large yield of metals and dust for this system. So thank you very much for listening. And yeah, let me know if you have any questions.
Thank you so much. This was really interesting talk, as well as I really like the graphical representation of various different ideas.
Thank you.
Do we have any questions?
So we already have questions in the chat, yes. So great talk. So regarding the oxygen 3 to C2 ratio, is the abundance ratio of oxygen over carbon fixed in your cloudy model?
So that's a very good question. It is fixed in these models that I'm showing here, but we have explored varying their that ratio. So of course, when you lower the C over O ratio, you expect that to translate through into higher oxygen 3 over C2 ratios. I think our main conclusion, though, is especially through the C2 line, the C2 line is just influenced by so many different variables. So it can be produced in neutral gas, but also in ionized gas. So it depends on the ionization parameter, the metallicity, things like the C over O ratio. And so this ratio you can really kind of play around with quite easily by tuning different parameters. But I think our main conclusion here is that if you just zoom in on the oxygen line, you get these, surprisingly high values compared to the models.
Okay, so the question was actually much longer, so I just cut half. So I continue with the rest of the question now. So have you considered the correlation between the galaxy ages and chemical enrichment? Because carbon and oxygen are released from different stars at different stages. So will it affect the line intensity ratio?
Yeah, it will. And this kind of goes back to that C over O ratio, because, exactly because of the different origins of those elements. So carbon is produced more dominantly by AGB stars, which take a longer time. You expect the C over O ratio to be low at the beginning, but then ramp up over time. So yeah, that I definitely expect that to play a role. The thing is, from our measurements, we can't really measure the metallicity of each individual system very precisely yet. There will be James Webb observations of some of them coming out, so that would be really interesting to look at. But yeah, we can't measure metallicities for individual sources very accurately yet, at least. And also the ages are difficult to measure.
Thank you so much. There are a couple of more questions, but I think we are running out of time. So
Okay.
move to Slack and you can answer them further.
Yeah, perfect. Thank you.